Hello, welcome to another in my series of videos on statistics, probability, and data analysis. This video was originally recorded in the fall of 2019 for my Computer Modeling and Data Analysis 2014 class, Data Matter, at Virginia Tech. Today we're going to look at how to use a simulation to explore a particular permutation situation. In this case, we're going to explore a gender bias scenario and see how simulation in using R to do that can help us out. So the scenario that we're going to consider is a particular study, real study from 1972. University of North Carolina was helping a bank in North Carolina understand the possibility of gender equity in promotions. Had a workshop with 48 managers from the bank. These managers were given a resume and asked whether the candidate of the resume appeared to be qualified for promotion. This resume was identical among the 48 managers that received it, except 24 of the managers received that resume indicating that the candidate was male, and 24 of the managers received a resume that indicated the candidate was female. And then the 48 managers said, evaluate this resume that's in front of you and assess whether the person is qualified for promotion. So as it turns out, in this particular case, there were 35 managers who felt that the candidate was qualified for promotion. But of those 35, 21 of them happened to have a male candidate, and 14 had a female candidate. Or of the 24 male candidates, 21 of them were selected for promotion. And of the 24 female candidates, 14 were selected for promotion. Remember, these resumes are identical, except for the indication of the gender of the applicant. Well, that looks to be rather lopsided. The male candidates have a 21-3 odds, or 7-1 odds, of receiving the promotion, whereas the female candidates is 14-10, or 1.4-1 odds of receiving promotion. So the ratio between those, the way that we often summarize these kinds of scenarios is this odds ratio. The odds are 5 times greater, apparently, for the male candidate to be promoted as opposed to the female candidate. We randomly assigned these 48 resumes to the managers. Perhaps it's the case that 35 managers in the room happen to be inclined for this candidate to be promoted, and 13 do not feel this candidate is worthy of promotion. And if male or female hadn't been indicated, or they're completely blind to the gender of the candidate, it just happens that of the 35 managers who are inclined to consider this candidate qualified, 21 happened to indicate a female, or a male applicant, and 14 female. If we were to reassign the resumes to a different group of 48 managers in a parallel universe, as it were, maybe it would have shuffled out differently. Maybe it would have been 14 males and 21 females, as it turns out. Well, let's see how likely that might be. This idea of sort of natural variability is important in understanding the phenomenon in any statistical scenario. Well, R has a good way of doing this sort of shuffling for us. So in R, we can have a list of the 24 males and 24 females. We then, the sample function will shuffle a vector. And so then we'll have the 48 M's and F's shuffled again, and let's say the first 35 of them are the managers that in fact indicate the candidate is worthy of promotion. Let's see how this plays out in the real world scenario. So first we create our array of original males and females, and then we shuffle that array. And here we see there's some males and some females scattered throughout here. And now we wish to say there were 19 M's in the first 35 positions. Now notice what we've done here is this graded resume equal to M is actually a logical array. There's 35 trues and falses. We're able to add those up. We're able to do arithmetic with logical variables. And this little trick in R So true is used as a 1 and false is used as a 0. And in fact, there were 19 of these. Of course, we could do this again and see what we get. So a different shuffling, we get 15. Do it again, 19 again, 19 again, 20 this time. So we see in these handful of shuffles, we've had a couple 19s, a 20, maybe 21 isn't all that uncommon. So far we haven't hit it, but it still might happen. So this is where simulation comes in. We could sit here all day and replay these couple of commands and see how often do 21, 22, 23, 24 even occur, but that's why we have computers to do this kind of repeated task over and over for us. This is where simulation comes in. What I've got here is a general pattern of simulation, where you say, how many times do I want to simulate some phenomenon that I'm doing, and it has a randomization component to it in some way, and I run through a loop over the number of simulations I have that does some probabilistic simulation, and I store the results in this array that I've created of results, and then at the end of my simulation I look at what happened in the different scenarios. So in this case I'm going to do the experiment I just did, where I shuffle my 48 resumes and see of the 35 managers who are inclined to promotion, how many of those are males. And I'll do that 1,000 times, take that number each time, and see how many times we have for each of the candidates. So let's go back to R and set up this simulation. So there's how we started off. Notice this results of numeric numsim. This is just taking the setting up the results vector. You don't have to do that, but it does improve the performance of your simulation quite a bit. You can just have it work dynamically. And now we do the experiment. This is the work that gets done inside the loops. This will go 1,000 times because I set numsim to 1,000. And notice the only difference here is that instead of just looking at the sum of the graded resumes from 1 to 35 equal m, I store that into the ith element of the results array. So there we go, we just did it. That was 1,000 iterations. So now we use the table command to look at the results vector. Okay, so there was one time that there were 13 males and apparently 22 females. There were also 2 times of these 1,000 simulations that it was 22 males and 13 females. Of the 35 that happened to be in the managers that are likely. Most of the time it was 16, 17, 18, 19 resumes happened to fall into the hands of the 35 managers likely to indicate promotion. But there was 24 times that we had 21 or 22, 21 or more males in the selected pool. So it does happen, but how often is it really? So we could just, again, add the number of results greater than 21 and divide by the number of simulations. So about 2.5% of the time is when this happened. That's fairly uncommon if it's just due to the random chance. It's not impossible, but that's often what we run into in statistical situations. This is the logic of statistical hypothesis testing. We say, well, here's my null hypothesis, that there in fact is no gender equity bias. There's no bias in the gender of these pools. It just happens that the 35 managers who are likely to give a promotion happen to be dealt 21 males and 14 female candidates. Well, yes, that is possible. And if that were the case, then we just had a scenario, a phenomenon happen that happens about 2.5% of the time. Or we conclude that 2.5% of the time is pretty unlikely, and rather we would conclude that maybe there is some bias in the promotion process. So as it turns out, this particular scenario of how we permute the selections of one group into another is identical to a famous scenario in statistical literature. Ronald Fisher is a famous English statistician from the first half of the 20th century. He's at a tea party with his friend Lady Bristol. They pour the tea and are pouring milk into it, and Lady Bristol objects and says, you know, she can tell the difference. You must have the milk in the cup first and then pour the tea in. And Fisher and his friends are incredulous. They say, you can't possibly tell the difference. Oh, no, she insists, I can tell the difference. So Fisher devises this test where they have 8 cups of tea. In 4 of them, they pour the tea first and then add the milk. And in 4 of them, they do as Lady Bristol suggests, put the milk in the cup and then add the tea to it. They then shuffle the teacups and ask Lady Bristol if she can identify which of the 4 cups are the ones with milk first and which of the 4 cups had tea first. This is apparently a real tea party that happened, and Fisher reports this in his experimental design book that he writes about 15 years later in the 1930s. And this is what's called a permutation test. And in fact, you could go through all the possible permutations, and there's 8 factorial ways in which the cups could be laid out, but distinguishing between the 4 with milk and the 4 without milk is not nearly that number of permutations. Similarly to the resumes that we just had, it's just a larger group of things that we are permuting. But you can exhaustively say how many different cases might you choose the first 4 cups of tea with the milk first, and that's the exact number, the exact probability of choosing the 4 cups. And in fact, Fisher doesn't tell us the outcome of the experiment in his textbook. Apocryphally, Lady Bristol did in fact identify the 4 cups of tea with milk first, and by implication the 4 cups that had milk added to the tea. So there's the layout of it, and you can read more about Fisher's exact test and more about this lady tasting tea phenomenon. Very interesting book about the scenario and about statistical testing in general. Now let's do that for our case here. As it turns out, R has a function for doing Fisher's exact test, this permutation test that tells us exactly what the probability is of the scenario at hand. So in this case, we create the matrix of the outcomes. Okay. There we are. So there's the outcomes of the matrix itself, and that's what we feed to Fisher's test. So this is a statistical test. It tells us that the p-value of this test, or the probability that we see an observation as extreme as what was actually observed, is about 5% of the time. But in fact, this test would go for either direction, either as extreme as 21 males and 14 females, or 21 females and 14 males. If we want to test what we call the one-sided hypothesis of only what's the probability of 21 or more males and discount the other direction, then we set the alternative equal to greater in our Fisher test. And here we see that's about 2.5%. Again, the estimated odds ratio close to 5, slightly different in this particular case from the exact 5 that we computed earlier. But again, 2.5% of the time, we see an example shuffle that would have indicated that, which is very similar to the simulation scenario that we had. So in this case, we didn't have to do a simulation in order to know the exact answer to the problem. But in some cases, that's not the case, where we don't have an exact statistical test for a particular scenario, and so we use simulation to do that instead.